What is up, everybody? Jacob here as always, and today I want to show you how to make a variable voltage regulator. It is a great beginner project, and it's a fun thing to build, and it's really useful. You can do a lot of stuff with it, like make a lab power supply so that you can connect your breadboard and adjust the voltage to power things that use weird voltages. You can always use it to charge your laptop at a weird voltage of 19.5 volts, or just toy around with it. You can even make it adjustable to where, maybe you want to charge something one day or charge something different another day. You never know what you're going to want to do. So stay tuned and I'll show you guys how to make it. And before I continue on to the demonstration, I just want to tell you guys that down in the description there's going to be a table of contents that tells you where I start the theory and then where I start building and then the demonstration of how it works, so that you can kind of jump over or jump to whatever you need to watch, because this is going to have a lot of information in it. And I'm going to do that with my videos from this point forward, so if anybody is a regular and has watched all these videos, then at least now you know. So anyways, let's go ahead and dive in and see what makes this chip tick and how to use it. Okay, so before we get started, I just want to point out the new camera angle. How about that, huh? Isn't that beautiful? Straight down from up top. I'm proud of that. Alright, anyways, so today we're going to be taking a look at a variable voltage regulator. What we can do with this is actually adjust the voltage output to do many different things. We can connect the same, say, battery to charge your phone, and also run a 12 volt, say, Bluetooth speaker. You can use a different chip running at a different voltage to, say, charge your laptop at 19.5 volts. And you can have all of these different things all connected to the same power source that is one voltage, even though everything that it's connected to on the output are different voltages. And the way that we're going to do that here today is with a variable voltage regulator. The specific chip that we're going to be using is the LM317. Is actually an extremely simple chip. I had to do a little bit of research on it and how it works, and I came up with some schematics. We're going to be taking a look at this here today. I drew it up. We got our input coming in here, and then our adjustable output coming out over here. And then this is the LM317 here. But first, let's take a look at the data sheets here. They're going to be extremely helpful. So if you look right here, let me bring this closer to the camera. You can see that's this guy here. You can see if I can get it to focus on it. LM317. You can see that's this guy here, so let's lay it next to it just for reference. So you can see that first pin is going to be the adjustment pin, if we're looking at it here. That second middle pin is going to be the output, and the third pin is going to be the input. So pretty simple. 1, 2, and 3, adjust, output, input. So we can take a look at it here in the circuit, and you can see you would want to connect pins 1, 2, and 3 accordingly. So the first pin is going to be connected here. The second pin is going to be connected to the output going out to whatever you say you're charging your phone or what have you. And your third pin is going to want to be connected to the input voltage coming in. For today's demonstration, we're actually going to be using the full bridge rectifier that we built in the last episode, and the transformer that I have all set up. Before we take a look at this circuit, let's take a look at what we're going to be building on our breadboard. And you can see it's extremely simple. Excluding the wires, you can see there are 5 components. There are 2 cleaning capacitors. We have this 200 ohm resistor, a 5 kilo ohm variable resistor or potentiometer, and we have our LM317. That's it. That's how simple that is and how it's going to be here today. And then you have a couple of wires jumping from ground and what have you. But let's take a look at this circuit here. So we're going to have our 20 volts coming in, or really you can have all the way up to 30 to 40 volts. And if you take a look at our data sheet here, this is for the 317. You can see that right here. You can see output voltage 1.25 volts all the way up to 37 volts. And this chip wants us to have an input voltage that is roughly 2 to 3 volts higher than what we're putting out. So you can see the maximum input here is 40 volts and the maximum output is 37, and so that's a 3-volt difference you can see there. And it's the same thing with the input. It's a little bit off, but you can see the minimum input voltage is going to be 3 volts, and that's going to output 1.25 volts. You know, that's as small of a gap as you're going to want to have. And I've noticed that you really want to have as small of a gap of voltage as possible to reduce the heat output. The reason why this little chip has this hole here is so you can actually connect the heat sink, and that's why this is all metal, so they can transfer heat really well, because this will get hot. And there are ways to avoid that, and there's ways to avoid current even going through this, to have this regulate voltage but have something else regulate current. But we will take a look at that in another video. Today we're going to be just focusing on regulating voltage. So you can see that we have our voltage coming in here. This is our positive side and our negative side of our 20 volts. And that voltage is going to come in here just like this, and the first thing that it's going to do is it's going to charge this capacitor. This capacitor is not absolutely necessary, and neither is this capacitor over here, but what it does, if you guys remember from the last video, if you haven't watched it, I will link it down in the description. We talked about capacitors a little bit, and what this does, what a capacitor does, we'll just recap here pretty quickly. It almost acts like a battery. It's not a battery. The only common ground this holds with a battery is that it holds electricity inside of it, but that is it. So the first thing that this is going to do is it's going to charge this capacitor and put some electrical potential inside of here, and the negative side is going to pull electricity out this way, so that you have some potential here, so that in case if this were to fluctuate at all, you're still going to have, this can discharge if it needs to and come out and into this line here. So after it charges this capacitor here, it's going to go into the chip here, into the voltage in, which is pin 3. It's actually going to be this last pin all the way over here. So it's going to go in, and the first thing that it's going to do once it enters this chip here is it's actually going to go out of the out. And that's the next thing that it's going to do. It's going to leave the out. But you can see here that there is this connection that connects to a resistor. And if you remember from, again, I talked about this in the last episode, resistors resist the flow of current. So electricity is going to flow in through here, and it's going to travel across this resistor, and it's actually going to, because it's resisting the flow of current, and there is a connection to ground here, and current will be flowing, the voltage, which is basically the pressure, it's going to drop slightly. But really this resistor here is only to protect this from shorting out 100%, well, to protect our output from shorting out 100%. So this is to protect the 317 and not allow current to come flowing, you know, blasting out into the ground. So the next thing it's going to do is travel across this resistor, and there's a Y in the road here. So naturally there's ground here. We have this suction basically of energy. This energy is being sucked out to our negative here, and our positive here is pushing. It's pushing energy in this way, but this side is sucking energy out this direction. So naturally, this current, this voltage, electricity, it's going to want to go out to the suction. But as you can see here, we have this resistor, and this is a resistor, but it's slightly different from a regular resistor in the sense that you can adjust it. In this circumstance, it's going to be mechanically adjustable, so I can take a screwdriver and adjust what its value is, all the way from 0 to 5,000 ohms. So I can adjust it anywhere between there. So basically what that means is that there's a little connection over here to ground, and there's an adjuster that this can move back and forth and basically just touch somewhere on the resistor. So the further down this way it goes, the higher the resistance, and the closer this way, if it's all the way here and it's all the way at 0, then it's just a straight wire bridge all the way across the resistor. But if I connect it halfway, then it's going to be 25 or 2.5 kilo ohms and what have you. And this here, this is critical to the adjustment of our adjustable voltage regulator. You might be wondering why, and you might be wondering what exactly is happening here. Well, the way that this works, whatever voltage is present here, this chip here wants to make sure that the output is 1.25 volts higher than whatever is present right here. So if this is 5 volts, the output is going to be 6.25. If this input coming in here, if it's sensing 10 volts, then it's going to want to send out 11.25 volts. That is how this regulator works. And that's why it's almost magical. It's insane. Once I realized how this worked, it blew my mind. So we have this voltage here. This is slightly dropped a little bit, but that's not what is going to make this change happen. So let's say, for example, we have this full 20 volts coming out here. Okay? We have this 20 volts is coming in through here, and the moment it hits this resistor, we'll say that this is at 1,000 ohms. So I have it adjusted to 1,000, which is going to be, you know, roughly like right here. Okay? So this is 1,000 ohms, or 1 kilo ohm. And so this is going to have a resistance of 1,000 ohms, so it has to push that current through here. So there's still going to be some pressure left here. I haven't done the math, but if we look at the back here, this is the formula to find out. This is that 1.25 volts that this wants to keep above what's here. Okay? So the voltage out, whatever the output is going to be equal to 1.25 times this value here. And what this value here is, I'm not 100% sure what this 1 is, but it's just a part of the math. But this is going to be resistor 2 over resistor 1. So this here is going to be resistor 1, and this is going to be resistor 2. Okay? What this is going to do, when our electricity is flowing through here, the pressure is going to drop. The pressure here is going to drop because some of the electricity is being allowed to flow out to ground where the suction is. So it's going to suck a little bit, and so there's going to be less present here. So the voltage is going to drop a little bit, and especially here because it's after this resistor. So the voltage here is going to drop significantly. As the resistance increases here, less electricity can travel from voltage to ground, which means that the pressure increases. So the higher the resistance here, the higher the voltage here. And the higher the voltage here, the higher the voltage over here. So let's say, for example, that this is a 1,000 ohm resistor here. And this is going to remain 200 ohms. So remember, the 200 is resistor 1 and 1,000 is resistor 2. So we can plug that in here into our formula and find what our output voltage is going to be. So let's do 1.25 times 1 plus, and remember our resistor 2 was the variable resistor. So our variable resistor was 1,000 over 200. Okay, so resistor 2 and resistor 1, 200, 1,000. And when we do our math, 200 goes into 1,000 5 times. So we have 1 plus 5 times 1.25. And 1 plus 5 is 6 times 1.25 is 7.5. So 7.5 equals our voltage output. So with 1,000 ohms here and 200 ohms here, once this pressure has been built up and there's some pressure here, we're going to have that voltage present here, and it's going to flow in, and it's going to sense it inside of here, and it's going to output the corresponding voltage on the output, which is going to be 1.25 volts higher than what's present here. So if we have a 7.5 volt output here, so the input is going to be 6.25 with a 200 ohm resistor and a 1,000 ohm resistor down here. 6.25 volts will still be present after this voltage here. And then once this loop has taken place and we have our output voltage, now This is going to travel through here, and again we have this cleaning capacitor, and we all know what that does. It builds up a slight charge over here, while there's a suction on this side, and it pulls these particles out, the electricity, and it comes out this way, so that you have electricity sitting here, so that it kind of acts like a buffer to help clean the signal output. And now we have our adjustable output here, negative and positive. And if we were to adjust this, the higher the resistance, so let's say that we wanted this to be 2500 ohms. We wanted this adjustable resistor to be 2500 ohms, and this is going to stay 200. So we can just plug that in and play with it here. So 2500 divided by 200, or 25 divided by 2, is 12.5. So 1 plus 12.5 is going to equal 13.5. Then we have 1.25 times 13.5 equals 16.875 volts, which is going to be our voltage out. So in this circumstance, if this were 2500 ohms, this is going to end up being 16.875, which means that this over here would be 15.625. Okay, so that's going to be our output here, 7.5 volts, or depending on the resistance value here. And it's actually extremely, extremely simple. And that's all that we have here. So let's take a look at building this thing, huh? Okay, to build this thing, it's going to be pretty easy. We're just going to follow our schematic. So let's plug this thing into our breadboard here. I'm just going to plug it in into the middle. And on our schematic, that we have the voltage coming in, and where the voltage comes in, there's going to be a capacitor across the positive and negative, and that could really just go right here inside of our power bar here. So why don't we do that? We'll just jump it straight across from here to here, just to make sure that we have nice clean voltage coming in. This is just going to make sure it maintains a nice clean voltage. So now that we have this component here, let's take a look at the 317. So it looks like pin number 3 is going to be where our voltage comes in at. So why don't we connect our third pin over, which is going to be this here, the last pin all the way to this side, right here. We're going to connect that to our positive. Okay, now we have that connected to our positive on that last pin. Now we're going to connect our pin 1. That's going to get connected to ground, but we don't want to connect it directly to ground. We want to connect it through a variable resistor. And we're going to use this here. It's a 5 kilo ohm potentiometer, and it is a 20 turn, I believe. And you turn this little screw, and it increases and decreases the resistance. I'm going to connect one of the pins between the first pin of our chip, and then the middle pin I'm going to connect to ground. Okay, so we have this first, we have pin number 1 of our chip going through the potentiometer and then to ground, so that we have this going on here. But then the other side of that pin 1 needs to be connected to our pin number 2 through a resistor. And here I have a 200 ohm resistor that I'm going to go ahead and jump across from pin 1 to pin 2. In fact, we can do that on the back side. So I have that jumping across pin 1 and pin 2 to restrict the flow from pin 2 back to pin 1. And last but not least, we're going to go ahead and hook up this capacitor here. This capacitor is going to go across our output, which is pin number 2, and we're going to do that from pin 2 to ground. So I'm going to connect it to the back, and then go straight to ground with it. And our output pin being number 2, I'm just going to use this little jumper to jump that across so that I can access it a little bit easier. And I can access it from this row right here. So that is it. That's our entire setup. We're going to go ahead and hook it up to our bridge rectifier and put voltage across it. and we're going to see what it does. Let me go ahead and hook up some multimeters so that we can see what's going on. So this might look like a little bit of spaghetti here, but let me show you everything that's going on. So this multimeter here is going to be the voltage that is coming out of our full bridge rectifier so that we can see exactly what type of voltage we're transforming out of the wall. Then this multimeter here, let me turn it over to voltage. This is going to show the voltage that is actually coming out of our adjustable regulator here. Lastly, I have this multimeter hooked up to my pen probe, which I will probe around the breadboard, and we will analyze a few things and see everything that's going on here. Go ahead and turn this guy on and see what happens. Okay, so we can see here that the voltage coming out of our full bridge rectifier and transformer is 20.3, 20.4 volts. We can see the voltage that is coming out of our adjustable regulator. Looks like 4.9 to 5 volts. And I can just probe in here to verify that. 5.017 volts. Perfect. That's what we like to see. And we can see the adjust pin of the 317 chip should be 1.25 volts lower than what we just checked. This pin here, 3.5 volts. So that is just 1.5 volts lower. Let's see when I pull that out. It's because I'm putting a load on it with this LED, and so it's causing a little bit of feedback to happen. So the actual volt is dropping down to 4.7. So 4.7 down to 4.5 here. That is a 1.2 volt drop, which these multimeters are inexpensive. Let's drop this down a little bit. There we go, 5.01. Let's probe this in here. So 4.75 down to just below 3.5. That is exactly a 1.25 volt drop. Perfect. That's exactly what we're looking for here. And our output, if I can pin it right, peg it right, we can see our output is exactly 5 volts. Perfect. So I'm going to go ahead and hook up this multimeter directly to the board, and I'm going to hook this up in amperage mode so we can check the amperage that is going across our 317 chip. So I have the voltage coming out of the rectifier here, I have the voltage coming out of our 317 chip, and I have the amperage that's going across the 317 chip, and as you can see there is almost 0 amperage. Well, there is 0 amperage. So with 5 volts what we can do is we can actually, I have a little rig set up here, a positive and negative, and it actually goes to a USB. There we go, and you can see I can plug that into something and charge it. So let's take a look here and see what we can do. So I have a portable battery charger, and as you can see here, input 5 volts, maximum of 1 amp. So let's see. Let's take our positive and hook it up to our positive side here. Let's take our negative and hook it up to our negative side here. And let's see what happens when we plug it in. Now we can see we're reading 0.5 amps across the 317. And we can see we're maintaining this 5 volts. But you can see down here that our voltage coming out of the rectifier has dropped. And actually you can see that it's certainly charging. But what we're going to do is we're actually going to unplug this. And I'm going to take a thermometer here. It's about 90 degrees. So let's see what happens if we leave this plugged in. It starts to get hot. 130 degrees Fahrenheit, 134, 140, 150. So that's a problem, right? We can't have our chips getting that hot. So what you can do is you can hook up a heatsink. And I just so happen to have one lying around right here. But it's a little bit big. And for the purpose of this demonstration, it's not critical. I'm not going to attach a heatsink to this here. But what I am going to do is show you the adjustability. That it is, in fact, adjustable. So you can see I was able to charge at 5 volts. But let's say, we don't want to charge it at 5 volts. We don't have anything that we need for 5 volts, right? What is this? What is this? Phooey. We don't want that. We want 12 volts so we can run a Bluetooth speaker. All right? All that we need to do is go to our adjustable potentiometer here, and we can change its resistance value by changing this little screw. You can see as I screw it, the voltage declines. If I screw it the opposite direction, the voltage rises. So let's bring that bad boy up to about 12.2 volts, huh? 12.2 volts, perfect. Let's try to plug in something that uses 12 volts. And I just so happen to have this big, huge Bluetooth speaker here. It uses 1 amp, and I don't expect this thing to last very long because it would heat up this chip pretty quickly. But for demonstrational purposes and for science, let's do it. Hold my hand. You can see it takes this type of plug, and I'm just going to plug it directly into the breadboard using these two bad boys. I'm actually just going to use some alligator clips. I'm going to clip them to my probes so that I don't have to try to jam these big thick wires into these holes. Okay, so our positive is going to go here onto this bad boy. And our negative is going to go on this other side over here. Make sure they stay isolated from each other so that they don't touch and short out and explosions. I flipped the on switch on, and you can see that our voltage here from the rectifier has dropped slightly and that we're pulling 0.01 amps. So let's turn this thing on. Here we go. It turned on. It's got some fancy lights flashing on the front. I'm going to turn those off so that we can reduce our amperage a little bit here. There we go. I turned them off. You can see the amperage drops down. Let's see what happens when I connect it up to my computer and try to play some sound out of it. So I'm going to go ahead and start the music. And I have my computer set to 50% volume, and I have the speaker set to 30%. Our amperage kicks up just a little bit. Voltage drops a little bit, but you can see the output voltage of our chip has not fallen almost at all. So let's turn this up just a little bit. So I have the speaker at 50% volume. The maximum amperage output of this chip here is 1.5 amps. But that's with the heatsink in perfect conditions. So in a circumstance like this, it's going to get hot quick. Okay, this adjustable voltage regulator is extremely useful, and you can use it for other circumstances. For example, if you wanted to charge your laptop, you could adjust that screw, be sure that your input voltage is high enough, of course, and adjust your screw to make sure that you have the correct output voltage. My laptop takes 19.5 volts. You'd want to adjust that to roughly 19.5 volts. You would want to deal with the heat somehow, and this can only output 1.5 amps out of it across its input to output. And so you would need some way of increasing the amperage output. And there are several ways to do that. You can either get a larger chip that can handle higher amperage, or you can do what I will show in a future video, probably next week, how to connect a separate MOSFET to have it handle the amperage and have this handle the voltage, so that little to no amperage travels through this bad boy here, and all of the amperage, or most of it, travels through the amperage MOSFET. But there it is, that sweet and simple circuit. One of my favorite circuits so far, and it's a great project to do if you're just starting out. It's a good proof of concept, and it's a good way to learn and see what things do. So there it is. Alright guys, I really hope that you enjoyed this video. I loved explaining this to you guys. I'm actually building up to some pretty cool stuff, but I want to lay the groundwork instead of just diving into some crazy stuff. So be sure to stay tuned and let me know if I'm doing anything wrong, doing anything right, if you want me to change some stuff up, or if you just have some advice, or even just suggestions for other videos. I mean, if you have any questions about how things work or anything like that, just let me know down in the comments. I'm always here. I want to browse through them. So anyways, I'm glad you guys stuck around for this, and I hope to see you next time. Peace out.